Okay, okay, let's continue our class. Now let's talk about the use of contrast agents in radiographic examination. Can you hear me? Okay, let's continue our class. Let's talk about the use of contrast agents in radiographic examination. We use contrast agents to highlight specific organs and tissues that lack of natural contrast and make them easier to be seen and analyzed. By using this contrast agent will make artificial contrast between target organs and surrounding structures. And the contrast agent for radiography can be classified into two types according to their density. The first type is high density agent such as barium, iodinated contrast, and the second type is lower density agent such as air, carbon dioxide, and so on. The contrast agent can be introduced directly or indirectly. The direct introduction includes oral taking of contrast agent and a direct injection of contrast agent after puncture at the target area. And the indirect introduction is usually used in intravenous palligraphy. The contrast agent is intravenously injected first, and then they will be excreted by urinary tract. The introduced contrast agent fill either a hollow vessels or anatomic tubular structures and make them displayed. And this slide shows images of upper digestive tract radiography. In this examination, barium sulfate, a high-density contrast agent, is orally taken and fill the upper digestive tract, including the esophagus, stomach, and the duodenum, and make them display clear. You see this. You see the stomach here, esophagus, and also the duodenum. And this is an example of intravenous palligraphy. The image on the left is the plain film, of abdomen before injection of contrast agent, and the imaging on the right is a film of abdomen obtained after about 18 minutes after injection of contrast agent. On this image, the collection system of bilateral kidneys, ureters, and the bladder are filled with contrast agent and be displayed clearly. I think it's easy for you to understand, right? Okay. Now let's talk about fluoroscopy technique. In this technique, the transmit actually being filled on a fluorescent screen, resulting in a series of real-time dynamic images, which could be observed directly by the radiologist, who was protected from transmitted X-rays by a sheet of lead glass. It can be used without contrast agents and allow multi-angle and a dynamic observation of target organs. In fact, in the examination of digestive tract, as this picture shows, radiologists use fluoroscopy techniques to observe the digestive tract in real time from multiple angles before taking films. In this way, they can not only observe the contour of the digestive tract, but also evaluate their physiological movement. And the fluoroscopy sometimes is used to observe patients' respiratory movement and diastolic and systolic movement of heart. Let's see a short movie. from this movie, you can find that the fluoroscopy can be used to observe patients' respiratory movement and diastolic and systolic movement of heart. Okay, we have finished X-ray image. Now let's talk about computed tomography, CT. Today we just talk part of CT. It's part 1. Do you know who invented CT? No. CT was invented by Sir Godfrey Newport Hounsfield in the early 1970s. The invention of CT was considered by many to represent the greatest step forward in radiology since the discovery of X-rays. Together with Alan Cormack, Hounsfield was awarded the Nobel Prize in 1979 for his achievement. The first CT scanner were designed for head studies only, but soon whole body scanner became available as well. Today, CT has been widely used in the world, and any part of the body can be imaged by CT within a very short time period. And the new techniques of CT spring up frequently. So, but what is CT? CT is a computerized X-ray technique. It uses electronic system connected to a computer to capture and process the signals from X-rays that are passed through the body and construct a series of cross-sectional images of the scan area. And this schematic drawings show the tube detector system of CT scanner. This is the oldest type of CT. And during CT scan, for this tube detector system of CT, during the CT scan, the X-ray tube emits a narrow, fine-shaded beam of X-rays, which pass through a section of patient body and reach the array of detector, and the X-ray tube and the detector array rotate around the body of patients and acquire signals of X-ray attenuation from various angles. And the basic components of a CT system include scanner gantry, scanner table, computer displayer, and the memory storage and camera. The X-ray tube and detectors, locate inside this gantry, gantry. And during CT scan, a series of cross-sectional image of exam area are obtained. Each cross-sectional image represents a slice of the scan area, just like slices in a loaf of bread. The image process of each slice is just like to cut it into many uniform cuboid. It's called work cells. The image is composed of many work cells. And the attenuation coefficients of these work cells are calculated and arrayed as digital matrix by computer. And the final two-dimensional image is composed of pixels, which are displayed as the rectangular area with different degree scale. reflecting the attenuation coefficient of the work cells. Now let's talk about the characteristics of CT imaging. Remember the shortcoming of radiography? Imaging distortion, magnification, and overlapping of images from different structures. These are shortcomings of radiography. And the cross-sectional imaging method of CT make it avoid the shortcomings of radiography. And in addition, its density resolution is higher than that of X-ray. So CT is cross-sectional imaging with highest resolution of density. However, the spatial resolution of CT is inferior to traditional radiography because size of pixel. The spatial resolution of CT imaging is determined by the work cell size, which is equal to the size of pixel multiplied by the size thickness. And the pixel size is equal to the field of view divided by a matrix size. And the field of view is the size of the displayed image. And the image matrix comprised of columns and rows that define elements or pixels within an image. Now let's talk about CT number. In CT, differences in linear attenuation coefficients among tissues are responsible for CT image contrast. This attenuation coefficient is a measure of how easily a material can be penetrated by an incident energy beam. It quantifies how much the beam is weakened by the material it is passing through. CT number is X-ray attenuation value in the CT image. It's expressed in Hounsfield unit. It is the CT number is a normalized value of the calculated X-ray attenuation coefficient in image. And the CT number of the substance of interest is calculated using the following equation. Here, UW, UA, and U are linear attenuation coefficients of water, air, and the substance of interest. And in this unit system, water is assigned a value of 0, and air is assigned a value of -1000. The CT number of soft tissue is usually from 20 to 50 Hounsfield unit. And the CT number of fat is ranging from -70 to -90 Hounsfield unit. And the CT number of bone is the 1000 Hounsfield unit or above. So more than 2000 Hounsfield units are resolved by CT. Although more than 2000 Hounsfield units are resolved by CT, though you know the CT has a very high density resolution, and more than 200 units, Hounsfield units are resolved by CT. Although only more than 2000 Hounsfield units are resolved by CT due to its high density resolution, only 16 degree scales can be resolved by human eyes. So the windowing techniques must be used to change the appearance, including the brightness and the contrast of the image, so that the target structures can be highlighted. Here are two concepts you have to know. Window width. It is the range of CT number used image. Window level is the center of used CT number in the image. And the CT number range for the related window setting is from window level minus half window width to window level plus half window width. And the proper window width and the window level are essential for CT imaging. Now let's see the influence of window level and the window width on the CT image. This is an axial image of abdomen. You can see a liver, spleen, stomach filled with contrast agent, aorta, rib, spine, and just muscles, and so on. In the liver, there's a mass. It's hepatocellular carcinoma, HCC, hepatocellular carcinoma, HCC. And the window level for this image is 50 Hounsfield unit, and the window width is 100 Hounsfield unit. Now let's focus on liver. In this window setting, the CT number is from 0 to 100 Hounsfield unit, and it means in this image, any structures with CT number more than 100 will be white, and any structures with CT number smaller than 0 will be black. Remember that only 16-degree scale can be resolved by human eyes. And in this image, the single scale represents 0.25 Hounsfield unit. And the difference of CT number equal more than 6.2 Hounsfield unit can be resolved by naked eyes. Because the difference of CT number between normal liver and HCC, hepatocellular carcinoma, is about 10 Hounsfield unit. Therefore, in this image, we can find HCC, and differentiate it from normal liver tissue. So, proper window width and the window level for the detection of HCC on plan CT image are 100 Hounsfield unit and 50 Hounsfield unit respectively. Now let's see what happens when we use the same window level but a large window width. On this image, can you find HCC? Can you find hepatocellular carcinoma? No. Why? A wider window width will display a wider range of CT numbers. Consequently, the transition of dark to light structures will occur over a large transition area. This results in obscure contrast between tissues. In this image, the single grid scale represents 62 point. You know, for this in this window setting, the window width is 1000. The window level is 50. So in this image, the single grid scale represents 662.5 Hounsfield unit, much higher than that of CT number difference between the normal liver and the hepatocellular carcinoma. Therefore, cannot see HCC. So, do you understand what I'm talking about? So when you use the same window level but large window width, a single like this one with window width of 1000 and window level of 50 Hounsfield units, the single grid scale represents the single grid scale that can be resolved by our eyes represent 62.5 Hounsfield units. It's much higher than that of CT number between the normal liver and HCC. We just discussed on the above the earliest several slides. Okay, so this single grid scale is too large, and therefore there is an obscure contrast between the tissues, and for this reason you cannot see HCC. What happens when we use the same window level but small window width? Here, the window level is also 50, but window width is only 1. The window width is very narrow. And this means any pixel within CT value with CT value less than 50.5 looks white, and any pixels with CT value smaller than 49.5 looks black. And this means most of pixels are either white or black. And this results in very strong contrast of image. And this image looks very noisy. So this smart window width is not proper. Although you can find SCC, but this image is too noisy. So this window setting is also not proper. Now let's use the same window width for the high window level and see what happened. Here, window level with 1000 and the window width is 100. You cannot even see the lever, right? You cannot even see the lever because the lower CT number in this setting is 1000 minus half of window. The 1000 minus the half window width, that means 50. 1000 minus 50 is 950. So lower CT number in this setting is 950, and the CT number range of the target tissue is not in the range of window setting. Okay, in this image you can only see the bones. You cannot even see the liver. So therefore you cannot find the SCC because you cannot even find liver, right? So during CT examination, you should always use suitable window width and window level in order to clearly observe structures you want to see. For more examples, here are 3 images. They are all axial images of chest. This is the axial image of chest with the lung window setting. You can see the lung tissue, the bronchi, and the lung markings. That's right. And this is the window setting used for the observation of mediastinum structures. In this window setting, you cannot see the structures of lung, but the structures within mediastinum is showed more clearly than this one, right? And this window setting is used for observation of bone, ribs, scapular. Okay, compared with this image, the bone structure is are displayed much more clearly, right? So you should use for the examination of chest, you use the lung window setting for the observation of lung, and mediastinum window setting for the observation of mediastinum structures, and a bone window setting for the observation of bone structures. And now let's talk about the classification of CT. And according to the scanning pattern, the CT can be classified as conventional CT and a spiral CT. And spiral CT can be further classified as single slice CT and multi-slice spiral CT. This slide shows you the conventional CT. Conventional CT system use the cable take-up mechanism to deliver electrical power to the X-ray tube, and the stop and shoot technique is used for scanning. In this model, the CT system acquires a complete set of projection data while the object is stationary, then moves this object in the X-ray direction while the X-ray tube is off. then scans again, and so on. And there is a time loss between scan. This is the oldest type of CT. And later, spiral CT is developed. Spiral CT image acquisition was a major advance on the early stepwise method. During spiral CT scan, continuous axial tube rotation is used, along with continuous table incrementation to reconstruct a large number of slices covering a volume. From the perspective of patients, the axial beam from CT treats the spiral path. So it's called spiral CT or helical CT. And with the development of technology, linear array of detectors elements used in typical conventional and spiral CT scanner has been replaced by two-dimensional array of detector elements, which make multi-slice spiral CT possible. So this in the typical conventional and spiral CT scanner, they only use linear array detector elements, and later this two-dimensional array of detector elements are developed, and it makes this multi-slice spiral CT possible. In multi-slice spiral CT scanner can acquire images of multiple slices or sections simultaneously, and thereby greatly increase speed of CT image acquisition. And the smallest detail can be scanned within practicable scan times. And use modern multi-slice CT, patients don't even have to hold their breath during CT examination. And up to now, CT has undergone multiple improvements with an increase in the number of detectors and a decrease in the scan time. And nowadays, multi-slice CT enables a wide range of clinical applications, from three-dimensional to perfusion imaging to CT fluoroscopy. Now let's see a short movie. I'm not sure whether network allow playing it or not. If you cannot see it, tell me, we skip it. And this is a conventional single slice spiral CT with use a linear array of detector elements. And this is the early generation of multi-slice CT with only a few rows of detector. And this is the current multi-slice CT with as many as hundreds rows of detector, which can be used to perform 4D CT scan. What is 4D? Let's play it again. So what is 4D? The 4D means fourth dimension. The fourth dimension is time. So, and the current multi-slice CT can be used to do CT fluoroscopy. See, you can see the movement of heart. You can see the movement of heart. Okay, so CT has a much more development from the earlier conventional CT scanner nowadays. Okay, that's all for today's class. There are still more than 10 minutes before the end of this class. This is the time for answering your questions. If you have any questions, just ask me. I will answer answer questions right now, okay? If you have questions, just ask me. You can review the PPT and think about them. And if you have any questions, just ask me right now. We still have more than 10 minutes before the end of the class, so it's time for answering questions. Do you have any questions? Okay, let's make a brief summary for today's class. Today we talk about X-ray imaging and the part of CT imaging. In X-ray imaging, you have to know who discovered X-ray, okay? And you should know what is X-ray. It's high energy electromagnetic radiation. You should know what is X-ray, and you also know the characteristic of X-ray. It has a penetrating effect, photosensitivity, fluorescence effect, and ionizing effect. And you should know the principle of X-ray imaging. The essential factor of X-ray image formation involve the characteristic of X-ray and the characteristics of exam objects, and also the devices for visualization. And the influence of the tissue density and thickness has influence on X-ray imaging. Let's see. And you should know the difference between the fluorescent examination and radiographic X-ray film. You should know the difference between the fluorescent examination and radiographic examination. And you should know the shortcomings of radiograph, including overlapping, magnification, and distortion. And you should know that based on the image anticipation method, there are mainly two types of radiographic examination techniques: radiography and fluoroscopy. And you should know the difference between them. And you should know for radiography, there are ordinary projection, high QA projection, and soft active projection. And sometimes the contrast agent was used to highlight specific organs that lack natural contrast with surrounding structures. And the contrast agents can be high density or low density. And the contrast can be introduced directly or indirectly. Okay. And you should know who invented the CT. It's Huntsfield, Godfrey Newport Huntsfield. You should know the concept of CT. And you should know the characteristic of CT. It's cross-section imaging with high resolution of density. The spatial resolution of CT image is determined by the voxel cell. And you should also know the concept CT number of CT number. It's very important for understand the appearance of the examined object on CT. And you should know the concept of window width and window level, and how to set the proper window setting. That means the proper window width and window level. And this is very important for the clear display of the structure when observed. So this is a very important point for today's class: window width and window level. Okay, you should use suitable window width and window level in order to clearly observe the structure you want to see. And the classification of CT, the conventional CT and the spiral CT. Okay, we just make a short summary for today's class. Do you guys have any questions? I'm still ready for answer. I'm ready for answer questions right now. No, we don't have. Okay, I see a question. You don't have the book, but I'm going to upload the PPT. I'm going to upload to the group. I'm going to upload my PPT. Let's do it. I have already uploaded my PPT in the on the relative files. Can you find it and can open it? Can you open the PPT? Okay, I'm glad that you can open the PPT. And do you guys have any questions? I'm ready to answer your questions. Okay, if you don't have any questions, that's all for today's class. And I hope you review my PPT. And if you find some questions, you can send me email. You can find my email address on the first page of my PPT. And okay, thank you very much for your cooperation, attention in today's class. And see you on Friday. See you on Friday. That's all for today's class. You can leave. Thank you. Thank you very much.